Swap has changed rooms. And the next speaker of this session is Massin Guerdi about lambda-superposition tactic for Isabelle HOL. So the reverse. We had a talk about using Isabelle to verify superposition, and now it's using superposition for Isabelle.
Exactly, thanks. Yeah, so Isabelle HOL, it's a proof assistant based on higher order logic, which we just heard about. And Isabelle offers a very strong form of proof automation, which is provided by a tool called Sledgehammer. And Sledgehammer integrates high-performance external automated theorem provers into Isabelle. And instead of just blindly trusting the output of the external prover, Sledgehammer reconstructs the ATP proof within the Isabelle system using Isabelle's built-in tactics. The reason this works is because the tactics, they justify their proofs using the Isabelle logical kernel, so their proofs can always be trusted. And an additional benefit is that because the final proof script only contains tactics and no calls to the external automated theorem provers, it's always possible to recheck the formalization without having to have the automated theorem prover installed that originally discovered the proof. So today I will be talking about SLAM, which is a new lambda-superposition tactic for Isabelle HOL that I've developed. And it's primarily intended to improve Sledgehammer's proof reconstruction, particularly of proofs that were found by external automated theorem provers that target higher order logic. So to explain a bit how Sledgehammer works, of course it has many features, so this is only a single mode of operation and it's somewhat simplified. But what first happens is the user invokes Sledgehammer on a goal, and then a premise selector, or also called relevance filter, will try to identify suitable theorems and lemmas which might be useful in proving this goal. And then the goal and these facts that the premise selector has found are passed to the external automated theorem prover. And this theorem prover will then either succeed in a proof or not. But if it succeeds, Sledgehammer doesn't go into reconstruction immediately, but rather it repeatedly calls the external prover to try and minimize the set of facts that is necessary for the proof. And so the result of this process is a goal and a minimized set of facts. And this is then given to the metis tactic. And the reason why this works and why the premise filter doesn't go directly to the metis tactic is because the problem that metis has to solve is much easier than the problem that the external automated theorem prover initially had to solve, because now all the irrelevant facts are gone from the context. And of course, metis is not the only tactic that Sledgehammer calls for reconstruction purposes, but it's one that's particularly well suited because metis is itself built around an automated theorem prover internally. And so the result will then be an Isabelle proof because metis tightly integrates this automated theorem prover into Isabelle and justifies every single proof step. And that is the setting. The problem is that metis is an automated theorem prover that targets untyped first-order logic with equality. And this requires translating from Isabelle's logic into metis's logic using encodings of lambda expressions, for example, using lambda lifting or SK combinators. It needs to encode higher-order functions in partial application, for example, using an applicative encoding using a binary first-order function symbol. And it also has to encode types because metis's logic is untyped. And these encodings are inefficient, so they can limit metis's higher order reasoning abilities. Because, for example, if you have SK combinators, you have to reason about things like beta reduction, which happen automatically in a higher order system. So SLAM is a new higher order alternative to metis, and it's also an automated theorem prover, so metis and SLAM are quite similar in terms of architecture, but SLAM can natively reason about lambda expressions, higher order functions, partial application, and rank 1 polymorphism. So this is a perfect match for Isabelle's logic. And an additional thing that SLAM does is it also reasons about Booleans. So generally, provers reason about Booleans in the outer skeleton. So for example, we saw in Balázs's talk, we had clauses where there were disjunctions at the outer level, but if Booleans are somewhere deep inside of a term, then one has to axiomatize them, and SLAM is able to natively reason about them, in particular about quantifiers. And another difference is that while metis was originally developed independently of Isabelle and later integrated, SLAM builds directly upon existing Isabelle data structures, for example, the term data structure. The calculus provides inference rules and a redundancy criterion, and the concrete calculus used by SLAM is called Lambda-Superposition with Booleans, which was developed by Bandkamp et al. And this calculus extends first-order superposition to higher-order logic. And it's well established because it's used in the automated theorem provers E, Zipperposition, and in lean forced duper tactic, which plays a similar role to SLAM in lean. The way that, so just to quickly recap, we already saw this in the previous talk, but the way that superposition provers work is they are refutational. So they assume the negation of the goal and then attempt to derive a contradiction. And they do this by operating on a set of clauses which they saturate by repeatedly applying inference rules to derive new clauses, simplifying clauses in the set, and also removing redundant clauses. So the calculus provides inference rules to perform this reasoning, and the redundancy criterion determines when a clause can be removed or when a clause can be simplified, because a simplification just means that one takes one clause, deletes it, and replaces it by another. So it's also about redundancy. And this is repeated until a contradiction has been derived. The calculus used by SLAM is a refutationally complete calculus. So what this means is that whenever the initial set of clauses is unsatisfiable, then a fair application of the inference rules eventually yields a contradiction. SLAM, however, is a pragmatic implementation of the calculus. What this means is that it omits the most expensive inference rules of the calculus. It does not use full higher order unification, but rather Isabelle's built-in pre-unification algorithm. And also in SLAM, inferences can only have finitely many conclusions. I'll talk about that in a second. And these choices, they have some consequences. So one is it sacrifices refutational completeness, which is unfortunate, but they improve performance and they also simplify the implementation. So that's why. And yeah, so a bit of terminology. SLAM operates on Isabelle terms, which are write S or T. Literals are unordered equations or disequations of terms. Then clauses are unordered disjunctions of such literals. And finally, inference rules, they have a number of premises and derive a conclusion. So here's an example of an inference rule from the calculus, which is called equality resolution. It operates on a clause that has a negative literal, t is not equal to t prime. And it has a side condition, which is that sigma is a unifier of t and t prime. So applying sigma to the clause on the top will yield a clause with a negative literal t sigma not equal to t prime sigma, but the two terms are equal because it's a unifier, so this literal can be removed and the inference can conclude the conclusion C sigma. Now another important rule is the superposition rule. We saw an application of this in the previous talk, but here it is in generality. So the superposition rule operates on two clauses. The left premise is a clause that contains a positive equation t equals t prime, and the right clause is a clause which contains a subterm u. And the conclusion can be understood in the following way. So superposition essentially uses the left premise as a conditional rewrite rule to rewrite this subterm u and to replace it by the subterm t prime. But of course this happens in the instance, only in the instances of the left premise and the right premise where the terms t and u are actually equal. And these side conditions, they refer to higher order unification. So in first order unifications, the side conditions would be that sigma is the most general unifier of the two terms. In higher order unification, there aren't in general most general unifiers, but rather one has possibly infinite complete sets of unifiers. And what that means is that, for example, this equality resolution rule has to consider all unifiers in this possibly infinite complete set of unifiers, and that makes it an infinitary rule. So it's a rule that can have infinitely many conclusions, one for each of the unifiers. And this, of course, complicates the implementation because one has to maintain these inference rules as infinite streams and interleave those streams. So but if one evaluates this in practice, especially on Sledgehammer problems, usually it suffices to just take a small number, so for example, the first two unifiers or the first four, and so that's what I do in SLAM. And what is also done in the pragmatic modes of external provers like Zipperposition, for example, in the modes that are most successful in theorem proving competitions. Okay, so here's a rule that is specifically about higher order reasoning. So this is the argument congruence rule. It applies to literal that contains an equation of functions and concludes that if the two functions are equal, then they are equal on all arguments. So x is a fresh variable. And for an example of Boolean reasoning, the kind of Boolean reasoning that SLAM can perform, there's this rule, the exists rewrite rule, which applies to a clause that contains a universally quantified predicate and can replace this universal quantification by the application of the predicate to an appropriate Scolam constant. So we have seen these unification side conditions, and they are important to ensure soundness. But in addition to these, there are also side conditions that are used to prune the proof search. So for this, the calculus is parameterized by a literal selection function. This is a heuristic that is used to mark some of the literals of a clause as selected, and then inferences are restricted by side conditions to apply only to literals which are selected. And another important heuristic is the term order. This is a partial ordering on terms. And this is used, for example, to prevent superposition, if we view it as a conditional rewrite rule, from replacing one term by another term which is already known to be greater. And it is also used in simplifications. For example, if we have a unit clause, so that's a clause consisting of only one literal, and we have an instance where one of the two sides is greater than the other, then we can use this unit clause to perform in-place rewrites in other clauses. And the term order used in SLAM is a higher order Knuth-Bendix order, which was developed together with the original calculus. Okay, so here's a high-level view of how SLAM works internally. So there's first a proof search, which plays a similar role to Metis's internal automated theorem prover. And this proof search operates on a custom clause data structure, which uses Isabelle terms, but these terms are, for example, not type-checked during the proof search, and also the clauses are not proven to be correct. But once the proof search has found a derivation of the contradiction, then it passes this derivation along to a proof reconstruction module. And this proof reconstruction module then interacts with the kernel and replace the derivation to justify every step that was done during the proof search, and finally the proof of false is obtained, and then the proof by contradiction can finish. And the reason for this split into two phases is that typically during the proof search, the prover will have to discover many more clauses than actually contribute to the derivation of false in the end. And so the somewhat slower interaction with the kernel is reserved for the proof reconstruction phase, where then only the clauses that actually matter for the contradiction are reconstructed. So the proof reconstruction works as follows. So given a goal G, we now have a derivation of false from the negation of G. That's what the proof search gives us. And then the proof reconstruction replaces this derivation using the kernel by first assuming the theorem, not G, and changing the goal to false. And then every single inference step is replayed, where clauses now become proven Isabelle theorems. And finally, the theorem false is produced, and the goal can be closed. And to replay these individual inferences, the proof search records the premises, unifiers, and any newly introduced terms, such as fresh variables or Skolem constants, for every clause. And then if we have, for example, during the search, such a binary inference rule, during the reconstruction, we can split this typically into two phases. So first, we instantiate the premises which are now available as theorems. So we call a kernel function that performs this instantiation on a theorem and gives us back a theorem. And then we can perform a simpler version of this same inference, with the difference being that where this inference had to perform unification, this simpler variant of the inference now sees identical terms because the two clauses have already been instantiated. So we save the work of having to do unification twice. Okay, so quickly for the evaluation, I compared SLAM and metis as proof reconstruction backends for Sledgehammer. For this, I randomly chose 8,000 goals from the archive of formal proofs. And then for each goal, I ran Sledgehammer with Zipperposition as the external ATP because it's the one that has fairly strong higher order capabilities and uses a similar calculus to SLAM. And Zipperposition manages to prove 47% of these 8,000 goals. And then I use both SLAM and metis and attempt to reconstruct these 47%. So here are the results. Metis, the baseline is quite strong, so it manages to reconstruct 88.7% of proofs. SLAM, unfortunately, only manages 78.9%, so it's around 10% less. But there are 30 goals that only SLAM could prove, or rather 30 proofs that only SLAM could reconstruct. So if we take the union, we do actually get an improvement of 0.8 percentage points over metis alone. And to better understand this difference between metis and SLAM, I looked at the time they took to reconstruct proofs. So here we have metis on the x-axis, SLAM on the y-axis, and we see this big cloud here, which corresponds to proofs where SLAM was slower than metis. So in conclusion, metis generally performs better than SLAM in terms of how long it takes, but SLAM's improved higher order reasoning does enable it to reconstruct some proofs where metis fails, and also enables faster reconstruction of some proofs where metis is slower, which we can see from these points here below the red diagonal. Yeah, finally, there's a bit of future work. So the first one is to make SLAM available to Sledgehammer users, either in the official Isabelle distribution or in the archive of formal proofs. There's some experimentation with heuristics that still needs to be done. And finally, we saw that there's a performance difference, but there's a lot of performance improvements that could still be done in SLAM. Yeah, that's it. Thanks.
Questions?
Thanks, this is very nice. I look forward to using or getting the SLAM proofs out of Sledgehammer. How does SLAM perform on first order problems or first order proofs? Probably the majority of those proofs are just first order. right? If metis manages to.
So I didn't specifically test on first order problems, but if we look at this, so here we have metis time on the x-axis and SLAM time on the y-axis, and what we see is that already, this is in milliseconds. So these are the proofs here that take metis 10 milliseconds, and SLAM can already take up to 100 milliseconds on some of those. So I think that suggests that there's really a significant difference in first order performance. And I think improving this, like closing this gap in first order performance should also make SLAM better at higher order reasoning and hopefully able to reconstruct more of these higher order proofs that metis really fails on. Yeah, thanks.
Do you have an idea where this performance difference could come from?
Yeah, so there's definitely a few things just in the implementation that could be improved. There's also a bit of an issue with the unification algorithm, because I'm just using Isabelle's built-in unification algorithm, which was not built for automated theorem proving. So I think that's one place to investigate further and to see if maybe this algorithm can be controlled a little bit better, or maybe it just has to be re-implemented.
Perhaps I missed it, but how many of these proofs were using higher order features?
Do you mean these 30 proofs, or?
Yeah, I guess the 30 proofs were using higher order, but what about the others?
Okay. The question is about these 8,000, right?
Yeah.
Okay. Yeah, I didn't specifically measure this or pre-filter them. I think this is something, that should also be investigated. Would be interesting to know if, one would have to find a way to detect whether a proof contains higher order features, but should be possible. Yeah, it's interesting.
Okay, then let's thank Massin.
Thanks.